Hey there, and welcome. Today, we're going to get our hands dirty with a classic collision problem from Irodov number 1.172. We're going to break this thing down piece by piece, not just to get an answer, but to really build up that problem-solving muscle you can use for pretty much any collision problem that gets thrown your way.
Okay, so here's how we're going to tackle this thing. First, we'll get the lay of the land, what's actually happening in the collision. Then we'll bring in the two heavy hitters of physics, conservation of momentum and energy. After that, it's just a little bit of algebra to get our answer, and then, the most important part, we'll figure out what that answer actually means. Let's do it.
Okay, first things first. Before you even think about writing down an equation, the number one rule in physics is to get organized. You got to understand the situation, lay out all your clues, and know exactly what you're trying to find.
So what's our setup here? We've got two particles, and the problem tells us they have the exact same mass, which we'll just call m. Particle 1 is zipping along at 10 meters per second. It slams, head-on, into particle 2, which is just sitting there minding its own business. Our job? Find the final velocity of that first particle. And right here, this is the golden ticket. The key clue that tells us this isn't just any old collision. 1% of the kinetic energy vanishes. We're going to come back to that.
All right, now for the first big principle. Seriously, anytime you see the word collision in a physics problem, your brain should light up with one word: momentum. It is always your starting point.
So what does that actually mean? Well, think about a game of pool. Right before you break, all the balls are just sitting there. The total momentum of the whole system is zero. Then, whack, you break, balls go flying everywhere. But, and this is the cool part, if you could magically add up the momentum of every single one of those moving balls, the grand total would still be zero. The momentum of the system as a whole doesn't change. It's a fundamental rule of the universe.
And this is where the magic happens. We take that big idea and we turn it into math. The momentum before is just the mass of particle 1 times its velocity. The momentum after is the momentum of particle 1 plus the momentum of particle 2. And since the masses are all the same, we can just cancel them out, which gives us this beautifully simple equation. This is our first major piece of the puzzle.
Okay, let's circle back to that clue I mentioned, that 1% energy loss. This is a huge piece of the puzzle because it tells us exactly what kind of collision we're dealing with.
Now, this is super important, and it's a place where a lot of people get tripped up. In a perfect world, in a perfectly bouncy, elastic collision, kinetic energy is conserved. But our problem explicitly says we lose energy. That makes it an inelastic collision. Think less of two billiard balls clicking and more of a car crash where you hear a crunch and see bent metal. That's energy being lost to the environment. You can't just assume every collision is elastic.
So to actually use that energy loss information, we need to know how to calculate kinetic energy in the first place, right? And here's the formula you probably remember. It's 1/2 times the mass times the velocity squared. This is the tool we'll use to count up the energy before and after.
Okay, makes sense, right? If we lose 1% of the energy, what's left? 99%. And we can write that out mathematically. The total final kinetic energy is just 99%, or 1 minus eta of the initial energy. And bam, we have our second equation. Now we've got two equations and two unknowns, which means this puzzle is officially solvable.
Okay, deep breath. We've done the hard physics thinking. Now it's just a matter of following the math. We have a system of two equations and two things we don't know. We can totally solve this. So here's our plan of attack. We're going to grab that first momentum equation and rearrange it to get the second particle's velocity, v2 prime, all by itself. Then we take that whole expression and we plug it right into our energy equation. It's going to look a little messy for a second. You'll end up with what's called a quadratic equation, but it's going to simplify down and give us exactly what we're looking for.
All right, so after all that algebra, after we solve that quadratic equation, we get our answer. So what actually happened to particle 1 after it made the hit?
Let's break it down. First up, the magnitude. In simple terms, how fast is it moving now?
And the number we get is 0.5 meters per second. Now think about that. It started at 10 meters per second, so it slowed way down after that collision. But here's the other really important part. The sign. It's a positive number. In physics, that sign is everything. It tells us the direction. So a positive result means particle 1 didn't bounce backward. Nope, it just kept on chugging forward in the same direction, but it handed off most of its speed and energy to particle 2.
And there you have it. We solved the problem. But you know, getting the right answer is only half the battle. The real win is having a strategy, a toolkit,
that you can use on the next problem and the one after that.
And this is basically it, your go-to checklist for collision problems. First, get organized. What do you know? What do you need? Always, always, always start with conservation of momentum. Then, you gotta ask, is the collision elastic or inelastic? That's your key to using the energy equations correctly. After that, it's just setting up your system, solving it, and this is a big one, thinking about what your answer actually means in the real world.
All right. To really cement this in your brain, I'll leave you with a little something to think about. We did all this assuming the masses were the same. But what if they weren't? What if particle 1 was a bowling ball and particle 2 was a ping pong ball? How would that change our equations? Mulling that over is a fantastic way to check if you've really got these concepts down. Thanks so much for joining me.